This digital clock is not running on software nor a loop. It's not even running on a microcontroller timer, whether it's GPIO or SysTick, none of those. Instead, this digital clock is running purely on hardware logic running in parallel on an FPGA. And with this clock, you can adjust the time by its minutes, hours, or even the format from military to regular or regular to military, vice versa essentially. As you guys know, FPGAs rely on hardware logic, while microcontrollers give you the ability to use timers and interrupts. But since we're using an FPGA, which have no built-in timers, we'll actually have to create our own timers. And to do that, we'll actually have to rely on the system clock to count one tick. One tick meaning 1 second of the clock speed has passed, and this will be one of the building blocks for counting our seconds, minutes, and hours for our digital clock project. What's up guys, my name is Lance, and if you're new to this channel, please hit that like button and subscribe to my channel so you'll see more content just like this. And in this video, we'll be going over the problem we'll be solving, our system block diagram, our code showing our logic and how everything works, and the final demo. And without further ado, let's get into it. So the FPGA we'll be using is a DE2115 from Terasic, which comes with 8 7-segment displays, 18 switches, as well as 4 push-button switches. It also comes with 3 onboard 50 MHz oscillators, as well as a 27 MHz clock for the TV decoder. But for the sake of this project, we'll actually be using one of the 3 50 MHz oscillators from the FPGA. So our objective is not only to build a digital clock, but like I mentioned earlier, one of our objectives is to actually build a timer using the system's clock speed. And again, our DE2115 runs at 50 MHz, so that equals to 50 million cycles per second. And the challenge is, how do we exactly divide that into one tick? And this is especially important for our counters. And another challenge is about counting seconds, minutes, and hours. So we'll have to create counters that rely on carry logic, which you'll see later. So for this project, we'll be combining synchronous logic for the counters with assistance from combinational logic. And without further ado, let's get into it. Alright, so here's our block diagram, and on top actually is kind of like a counter that I wanted to base up my project off. So originally I wanted to just make a simple counter that goes from 0 to 60, and I forgot to add like a multiplexer, like an if statement for when it reaches 60, then it would go back to 0. It's a synchronous logic here. I use like a clock, of course, because again, this is synchronous logic, and minutes is like the variable that goes from 0 to 60, like because it always gets incremented 1 by 1, like when reset is not hit, because we are using a reset switch, and whenever we hit that, like minutes goes back to 0, as you can see right there. But otherwise it will keep incrementing and incrementing. But I decided to take it a step further and create this beautiful graph that I made, which is also a rough draft, but yeah, like here is for generating like 1 hertz, like whenever 50 megahertz has passed for 1 second, then we create 1 hertz, and we use carryover logic for second ones, telling second ones that 50 megahertz has passed. The ones and seconds gets sent to the hex display driver, and then we also do another carryover logic to seconds tens, which also gets sent to the hex display driver. And same thing with minute ones, minute tens. I don't have enough space, so I decided to extend it here for minutes tens carry. Yeah, like I decided to split it in 2 because I want these 2 to run in parallel, where I want to do both military and regular standard time. So the user has the freedom to choose whatever format they want. But here's like for the hours and ones and the hours and tens, as well as the selector. So whatever they select, like whether it's military or regular standard, it gets sent to the hex display. I also drew these diagrams like for each line, but I just don't want to be going over too much detail because I want to keep the video short. So I'll show each one of these like as we go over the code. So yeah, but if you guys want to like pause and take a screenshot, then you guys can definitely do so. Like although I wouldn't recommend copying my exact digital clock. Alright guys, so here is our code. So here's my top level module, which is the digital clock, which creates an instance of the AM and PM hex display driver, like as you can see right here, as well as our regular hex display driver for, like, you know, the digits for the numbers, as well as the selector file for switching between military and regular standard time. And back to our top level module, I have 3 inputs. So one is the 50 megahertz clock, 4 are actually the buttons, although I only use 3 of them, and switches, like 18 switches of them, but I only use 1, as well as our hex displays. So hex 0 is used for showing AM or PM when using regular standard, but otherwise it's off. Hex 2 and 3 are for the second essentially, and hex 4 and 5 are for the minutes, and hex 6 and 7, here we go again with the jokes, are for the hours. So yeah, please no 6-7 jokes in the comments. And below that, I also made variables, as you can see right here, for simplicity's sake. So one is for the hertz, which you'll see later, for generating like 1 hertz tick. But let's get into like the inputs. So switch 0 is used for switching between formats. And like also decided to make a wire for selected format, which you'll see later. Key 0 is used as our reset for resetting the clock. Key, like, by the way, there's an odd symbol because all of the keys are in active low. Key 1 is used for adjusting the time for the minutes. And key 2, if you really want to go fast with adjusting the time, that's used for the hours. So onto our code. Here I have 2 blocks. So one combinational, like as you can see right there, and one synchronous, also as you can see right there. So the conditional block is used for adjusting the speed for time adjustment. So if key 1 is pressed, then 500 kilohertz is all the counter needs to go up to, or if key 2 is pressed, then it only goes up to 5 kilohertz, and that's pretty fast for adjusting the hours. Otherwise, when it's at idle, it runs at 50 megahertz, as you can see right there. And here is our counter, the synchronous block, I mean. So this is for generating 1 tick, essentially, hence the tick 1 hertz wire. Whenever it reaches 50 megahertz, or 500 kilohertz, or 5 kilohertz, then it would generate 1 tick pulse, as you can see right there, which is useful for the other counters we'll see later. But otherwise, it just keeps incrementing to either 500 kilohertz, 5 kilohertz, or 50 megahertz, depending whether you're pressing key 1 or key 2, like adjusting the time or not. And now onto our seconds blocks, which everything is in BCD format. So for the seconds, minutes, hours, everything's in BCD style. So yeah, we have 2 blocks. One showing the ones in seconds, as you can see right here. So from 0 to 9 essentially, and one for the tenths in seconds, which goes from 0 to 50. I accidentally put 60 right there, so I'm just going to adjust that. So as you can see here is our seconds ones carry logic. So if we are at 9 seconds and 1 tick pulse happens where we immediately go to 10 seconds, then the ones in seconds goes back to 0, and the seconds ones goes to 10. So that's our carryover logic. Essentially, it's telling the counter, hey, we are now at 10 seconds, but yeah, it will keep incrementing to 9 each time for the ones in seconds, and up to 5 each time for the tenths in seconds. So yep. And this also applies for our minutes counters, the ones in minutes, as you can see right there, and the tenths in minutes, as you can see right there. But this is where our minute tenths carry comes in. It's kind of like the special child for our project here. So now for our hours, and here I decided to use 2 types of blocks. One for military standard, as you can see right here, from lines 127 to 163, if you include comments, and one for regular standard from 166 to 202. So both are running in parallel, at the exact same time, because again, we are using an FPGA right here. So for the military standard time, the carryover logic pretty much works the same way, as you can see right here. Like 1's carry, I decided to not use 10's carry because, well, we don't really need it. But everything works the same way as the seconds and minutes, except that I had to make a carry logic, a special one for reaching like 24 hours. So when 24 hours has reached and it says 23:59:59 on the clock, and then a tick pulse happens, then it goes back to 00:00:00 on all hex displays. Whenever it reaches 0, then it goes all the way to 0, so you can see right there. And what about for our regular standard? You guys may be asking, like, Lance, why did he create a carry logic for reaching 1 o'clock but not 12 o'clock? We'll get into that later, actually. So if we are at 12:59:59, we want to go into 1:00:00, not 13:00:00, because there's no such thing as 13 p.m. Unless you're in some planet that has like 26-hour daytime. Maybe Pandora and Avatar has that. I think their day-night cycle is like 26 hours in Pandora, but okay, let's not get off track. And our hour 1's carry regular, like everything works the same. Now, if I reset it, however, minutes 1's gets set as 2, and minutes 1's regular gets set as 1. Like because there's no such thing as 0 a.m. or 0 p.m. Yeah, we want to make it as 12:00:00. So yeah, like everything here works pretty much the same. Now for determining our AM and PM. So here, this is where I decided to create our special carry logic for 12 a.m. or p.m. That's where both the military standard time will be used to toggle AM and PM. So if it reaches 12:00, then you set it to PM, as you can see right here. So if AM_PM is 1, then that means we are in the PM range, like 12 p.m. to 11:59 p.m. And if we reach 24 hours, which gets reset back to 00:00, then AM and PM gets set to 0, which indicates AM. And that goes into our hex display driver, the custom one that I made right here, as you can see right there. So here it is for AM, and here it is for PM. And the on and off one we'll get into shortly. If this is on, only for regular standard time, then all of this gets enabled. But otherwise, if we're using military standard time, all segments are off. Alright, so now into our format selection. So when switch 0 goes into a selector module, and based on that, I choose which hour digits goes into the hex display drivers. So as you can see right here, I made 2 registers, selected 1's hours and selected 10's hours. Okay, I didn't mention it correctly, but yeah, the selected ones, the ones with selected, goes into the hex displays for for the hours. So hex 6 and hex 7. So whatever's selected, it gets displayed. So you either get to choose between military standard time or regular standard time. And by the way, on and off, if you're using military standard time, like I said again, it won't show AM or PM. But if it's using regular standard time, then it will show AM or PM. And what does our selector look like? Because I wanted to keep things simple, here it is. So it's basically just assigning the output as the input. Alright, and finally for our hex display drivers, here it is. So seconds 1's, which are being counted by the way, which you saw earlier, goes into hex 2, and seconds 10's goes into hex 3, minute 1's goes into hex 4, minute 10's goes into hex 5, hour 1's goes into hex 6, whatever you select, or hour 7, hours 10's goes into hex 7. So here, if you want to see our hex display driver, my hex display driver I mean, Here it is. All right, now on to our demo. So it is 10:31 p.m. right now, and if I want to use military standard time, I can just toggle it with a switch. And if I want to set it back to regular time, I toggle it. So yeah, if it says P, that means it's PM. If it says A, that means it's AM. So let me show you real quick. So if I just wind up the time, like so it's 11:52, and let me just go up to 12 a.m. for example, it switches to 12 a.m. And if I want to switch back to military standard time, it disappears because, well, it's military standard time. You don't really need it. And if let's say I want to reset, does it go back to 12 a.m.? It sure does. And if I want to use military standard time, of course, I can just pull up switch 0, as you saw in my code. So, yeah. So it's going to be the same for the first 12 hours. Well, aside from, 12 a.m., it's going to say 00 in military standard time. So, yeah, let's say it's like 4:13. Boom. 4:13 p.m. Pretty cool, huh? Alright, we just completed our digital clock. So now you can switch between military standard time or regular time, if that's more your thing. And you can also reset it here, like that. And if you want to speed it up so you can adjust the time, you can definitely do so. And you have two options, either for a slower adjustment, which is more for the minutes, or for the hours. So overall, I'm very happy with this project. We have pretty much demonstrated how digital systems can be designed from both counters from synchronous logic, which is also assisted by combinational logic, and from dividing the 50 MHz clock from the FPGA wisely, we can create a stable, human-readable digital clock. And this design is simple, but it lays the foundation for more advanced systems, which can be alarm clocks, stopwatches, scoreboards, or even real-time embedded controllers. I love FPGAs because of its parallelism, oh gosh, that's so hard to pronounce, and deterministic timing. And this clock is a small but practical example of that, and I can't wait to do more with FPGAs. Maybe I'll buy a Xilinx FPGA, and you'll see more of that in the future. Anyways, that does it for this video. What are your thoughts in the comments below? Did you like this digital clock? Or are there things you could have improved on with my Verilog code? Just let me know in the comment section below, and I'll be very happy to answer. And once again, please hit that like button and subscribe to my channel if you haven't done so already. And until next time, I'll see you in the next video.